Hello everyone, welcome back to the channel. I hope you guys are doing amazing. So today's daily challenge on Leetcode is mostly a combinatorics problem. It consists of binary exponentiation and mod inverse also. So if you don't know this concept, just stay with me. I will explain you everything in great detail, and I will also show the implementation of all. Okay. So the problem says count the number of arrays with k matching adjacent elements. You are given three integers n, m, and k, and a good array of size n is defined as follows. Each element in array is inclusive in the range of 1 to m. Okay, so you have an n length array. You can fill each element with elements from 1 to m. You can fill integers from 1 to m, and exactly k of those indices should satisfy the condition arr of I minus 1 equal to arr of I. So that means that the adjacent elements should be equal in exactly k of them, and remaining they must be unequal. This is the point here. So return the number of good arrays that can be formed. Since the answer may be very large, return it modulo 1 in 9 plus 7. We have some examples. N equal to 3, m equals to 2, k1. So you have k1 means only one place the array should have equal adjacent elements. Okay, so here 1 1 2 1 2 2 2 1 1 and 2 2 1. So answer is 4. So let's see. This is actually, it is very difficult to understand the problem by reading such small examples. So let's try to take some good example, and uh, let's say we take an example which is n equals to 12, m equals to 6, and we have, let's say, k equal to 4. Okay, let's say 4. So we have a 12 length array, and we can fill numbers from 1 to 6. Okay, it is clear. First of all, this much is clear. So let me draw a 12 length array. Okay, we have a 12 length array. 4 4 8 9 10 11 12. We have a 12 length array. Now you tell me how many such pair of indices are there. We need to take care that arr of I equals to arr of I minus 1. These kind of pairs we need to take care. Okay, and there must be k such pairs. So first of all, you have to tell me in an n length array of n equals to 12, how many such pairs exist? How many such total pairs exist? By taking care of no conditions. How many such pairs exist? You can see this is the first pair, this is the second pair, this is the third pair, and so on. We have the 11th pair. If you see, okay, since there are 12 dashes, there must be 11 pairs. Okay, so can you say that there must be n minus 1 pairs in total? Okay, out of these 11 pairs, can you say how many of them should have this this criteria, right? This array of the adjacent elements same. So how many of the pairs out of 11 pairs, I can say that out of 11 pairs, 11 pairs, 4 have adjacent elements equal. Okay, 4 have adjacent element equal, and 7 have unequal. Okay, 7 have unequal definitely. Okay, you must take care that 7 of them must have unequal. So if you try to calculate side by side, we are taking an example, but you also try to calculate the in terms of n and k, right? So you have k adjacent elements which are equals. Out of n minus 1, you subtract k. So this 7 is nothing but n minus k minus 1. Okay. Now you see 7 of them must have unequal pairs. So if I try to write the unequal pairs, let's say this is an unequal pair. This says that this element is different from this element. Let's say this is also an unequal pair. This is also an unequal pair. So can I draw a border? Can I draw a partition between these unequal pairs? Why I am drawing that? Because after drawing, I can say that there must be 7 such bars. There must be 7 such partitions. 7 such partitions, can I tell? Okay. And whenever I am crossing a partition, let's say I'm traversing the array from 0 to n minus 1, from left to right, I'm traversing in this way. Okay. Whenever I am crossing a partition, my element numbers get changed, and within the partition, all the numbers are same. Within this partition, all the numbers are same. Within this partition, all the numbers are same. So what I want to say is that only the 7 indices, only the 7 such pairs of indices, there exists a difference. There exist different numbers. All other pairs have equal numbers. You take any pair apart from this pair, they have equal numbers. You take this and this, they have equal numbers. This and this, again, they have equal numbers. So only at the partitions the numbers differ. In between the partitions, the numbers are same. You did understand this. You did understand this. And definitely this same number is different from this same number, because in this partition it is differing. Okay, so this is the catch. This is the main catch of the problem. You get 7 partitions. Okay, which was nothing but n minus k minus 1. We already told that n minus k minus 1 partitions you got. Okay, so now as you are traversing the array from 0 to n minus 1, you are seeing that I am getting 7 partitions. But how many such segments the array is divided into? This is one segment, this is one segment, this is one segment. Okay, so you can see that there will be one more segment than the partitions. There will be just one more segment. So there will be exactly n minus k segments. This much is also clear. Now you try to tell that how many ways can I select the partitions? So how many ways can I select the partitions? Out of these, first of all, or not the partitions, you can say that out of these pairs, n minus 1 total pairs, I have to select n minus k minus 1 pairs which have equal, or I can select k pairs, whatever, right? So I can say that out of these n minus 1 pairs, I can select n minus k minus 1 pairs. Okay, so I am choosing this. This is combination. Okay, I hope you know all the combinatorics stuff. Okay, I'm just assuming that you know what does NCR means. Okay, so out of this n minus 1 possibilities, I am choosing n minus k minus 1 possibilities. Okay, so I have chosen all the partitions. Now it is time to fill this array with elements. Now from 1 to m, I have m choices. I have this m choices. But for the first, you see, for the first iteration, I have m choices only. I multiply by m. For the next, I have m minus 1 choices, because this should be different from this, that at the partition, the numbers are changing. So it should not be the same number. Again, this should be different from the previous partition. So similarly, this m minus 1 will get repeated this partition number of times. This partition number of times. So m minus 1 get repeated n minus k minus 1 number of times. Okay, so what you do is n minus 1 c n minus k minus 1 into m and m minus 1 to the power n minus k minus 1. This is our answer. This is our straightforward answer. If you see, I hope it was easy to understand. Very easy, not at all difficult, not at all difficult. If you try to think it in the right way, it is not at all difficult, and with practice things will come easily. Okay, so but if you try to think now, how will this may be very large number, right? And you cannot just use the power function. You cannot just use the power function a to the power v. You cannot use it in built C++ library. You need to use something to save the time complexity. You need to something called binary exponentiation, a power v, which we need to write manually. Okay, which we need to write manually. So this is the answer which I will return. Okay, and you know that this is also nothing but n minus 1 factorial by n minus k minus 1 factorial by k factorial. I assuming you know the formula for NCR, which is nothing but n factorial by n minus r factorial and r factorial. Okay, I am assuming you know this formula. Okay, so now you need to also have a mod, right? It is called that mod of 1e9 plus 7, where mod is 1e9 plus 7. You need to have this. So you see, if a into b, I told you to apply mod, you know that it's nothing but a mod b, and this b mod, then this is whole mod. Okay, this is whole mod. This is whole mod. But for binary exponentiation, but for this inverse thing, if I tell you calculate this a by b mod, then you cannot tell that A mod divided by. So what you need to tell here is that this thing you can tell A mod multiplied by 1 by B whole mod. Now this 1 by B whole mod is given by Fermat's little theorem, which I will tell you. What is the statement of that theorem? I will tell you later. So first let us understand how to calculate this binary exponentiation. Okay, how to calculate this binary exponentiation. So our objective is to find A power B fastest possible way, in the fastest possible way. Even if B is very large, mod modulo. Okay, let's say B is very large, of the order of 1 in 9. You cannot just multiply A 1 in 9 times. Okay, you cannot just multiply A 1 in 9 times, and because it will result in TLE, right? And you do a mod every time, you cannot do that. So what you need to do? Let's take an example out of how to calculate this. Let's say you are calculating something 6 to the power 11. Okay. So what you need to have in binary exponentiation, you have a result, final result, which is initialized to 1. Okay. If you see 11, you try to break down this 11 into its binary form. This 11 is in decimal form. If you write it in binary form, it will be something like this. Okay. Now you try to iterate through the bits of this number, and you can definitely tell me that this is nothing but this. Okay, this is nothing but this 8 plus 4, 8 plus 2 plus 1. It can be written as this. So I can tell you that I can also write 6 power 11 as 6 power 8 into 6 power 2. Okay, 6 power 2 into 6 power 1. I can write it in this way. Okay, so I am removing all of this and just writing that this can be written as 6 power 8 into 6 power 2 into 6 power 1. Now you have a multiplier with you, okay? You have a multiplier with you. If you want to do A power B, you have a multiplier which was initially A only, okay? Which was initially A only. So if you traverse through all the bits of the number, okay? So this bits means to the power 0, which is nothing but 1. This bits mean to the power 1. This bit mean to the power 3, 2 to the power 3, okay? So you traverse through the bits of the number, and every time you get a 1, you multiply your result with multiplier. Okay, so what you do is that you get the 1 here, the result you get converted into 6. Okay, why 6? Because you get a 1 here. I see that this bit is set, and I am multiplying this 6, multiplying with this A. Okay, now you go to the next number, and every time you square this multiplier from A to A square to A power 4. So similarly, if you try to square this again, 6 square, you multiply it by 6 square. Since there is a bit high here, I will multiply it again to get 6 cube. Okay, now I get 6 cube. Now what is happening is that this bit is not set, this bit is off. So what I will do, 6 power 4, the next thing after 6 power 2, it comes 6 power 4, and then it will come 6 power 8. I will not multiply this because there was 1. I am iterating to the left of the bits. There was 1, 1. There it is 0. This is 1. So if there is 1 only, I will multiply the result, and I will, otherwise I will not. You see here the 6 power 3, it remains 6 power 3. I will not multiply it because the bit is low. Now again the bit is high. I will multiply it with 6 power 8. I will get 6 power 11. So this is how I get my result in binary exponentiation. This is how I do the binary exponentiation. I will explain you the code also in great detail. Okay. Now, the Fermat little theorem. So first of all, if you want to calculate 1 by A mod, okay, where mod is prime, then Fermat little theorem says that you need to calculate binary exponentiation, nothing but binary exponentiation of A mod minus 2 whole mod. So this is nothing but A power mod minus 2 whole mod. If you don't know this theorem, so this is the Fermat little theorem obtained from Fermat. This is some corollary of Fermat little theorem also, I guess. You can just check it. I'm not sure, but you can just check this theorem out. Okay, that's how you need to calculate this mod inverse. And from mod inverse, if you have so let's say factorial in the bottom, you can just do 1 by factorial to get this mod inverse also. So Inverse factorial you can easily calculate. So let's try to calculate few stuffs. Okay. First of all, I will calculate binary exponentiation as I told. Okay. I will have a mod also here, int mod as a global variable, which I will use again and again. 1e9 plus 7. So now binary exponentiation, I need to calculate a power b. Okay. I need to calculate a power b in the fastest possible manner. So as I told you, I will initialize a result. I will initialize a result with 1. I have to see, I initialized this result with 1. Okay. Now, while this b, while b is true, I will left shift, I will topple one of the bits of b. What do I mean by this? My b was something like 1011, right? And I am iterating through these bits. So at first I check the last bit, then I right shift it, I get 101. Then again check the right bit, last bit, and again I right shift it, I get 10. Then again I right shift it. So in every step I'm right shifting the bits. Okay, so it's nothing but so 1011, just writing it clearly, 1010101. So you see, I am getting the bits. I'm getting the bits again and again. Oh, this is not 101. Okay, so this will be 10. This is 1. Okay, I'm getting the bits in the order of this by checking the last number and doing a right shift every time on the while loop. I need to do a right shift. Okay, so while b is not 0, I will do a right shift of b. Okay. Also, if the last bit of b is set, I'm iterating through the bits, right? I'm checking the last bit of b is set or not. It means that AND with 1. If you AND with 1, you just check whether the last bit of b is set or not. Then I will multiply our result. Okay, I will multiply my result with b, a, our multiplier a. Okay, and I will perform a mod. Now, again, in every iteration, as I told you, this multiplier thing, I need to multiply. This 6 power 2, 6 power 4, this will get 6 power 8. Every time it will get multiplied with itself. So this is nothing but, I can say that this is, if this is x, if this thing is x, this is nothing but x square, x into x. Then again I can say if this thing is x, this is nothing but x into x. Okay. This thing is, let's say, capital X, this is nothing but x into x. So every time we are just squaring it. So every time I'm just squaring a into a. Okay, I do have it. Yes. So I do have the multiplier ready. I just need to return result. Okay. We have return result modulo mod. Can have this modulo mod. Okay, I will define hash define long also. I've defined it earlier. This might exceed in some cases, so I will just ensure that it has a long. Okay, because this multiplication might exceed this integer range and might give error, right? So this is there. Now I guess everyone of you know how to calculate factorial. I don't need to explain it to you, right? So if someone asks you to calculate factorial of num, what you do? First you check that if num is 0 or num is 1, you return 1. Factorial of 0 and factorial of 1 is 1, and then you have a result here also. Okay, so you go all the way from int I equals to 2, I less than equals to num I plus, you multiply this result into I. Okay, so take the mod, don't forget it, and you return result. Okay, I think this is very easy. You know how to calculate factorial. Okay, from 1, I just keep multiplying this I. That's how I calculate factorial. Okay, as I told you, mod inverse gives me 1 by a mod value, right? So I have the mod inverse function, which will take a number a and tell me the mod inverse of that. So that is nothing but binary exponentiation of, according to the theorem, binary exponentiation of this a. This is a number theory theorem. You can just check it out. A to the power mod minus 2, as I told you. Okay. Now, how to calculate inverse factorial? Okay. inverse factorial of a number, let's say num, okay? First, you go and calculate the factorial. First, you go and calculate the factorial, right? So how will you calculate the factorial? Just do fact of num, okay? That's easy, that's very easy. Then you calculate the inverse, mod inverse. So anything factorial you need to calculate, anything inverse you need to calculate, just do mod inverse. Inverse factorial is nothing but mod inverse of the factorial. Okay. Okay. So I have it. And I just return this inverse factorial modulo mod. Okay. I have everything which I need. Okay. I will go and see my final expression, whatever was my final expression, because I need to write that, right? Okay. I have this. So I will first try to calculate this NCR value. Okay. So first of all, I will just try to get this NCR value, which will be nothing but n minus 1 factorial. I have this fact of n minus 1 factorial. Okay. Only I will perform a mod. Okay. These things you need to take care. And I have inverse factorial. In the inverse factorial, I have n minus k minus 1 and k. Okay. I have n minus k minus 1 in the inverse factorial. Okay. I have the n minus k minus 1. And I also have k minus 1, right? But k, only k. Okay. K. So I will have this also. And inverse factorial also has a k. Again, mod. So what you do, you can get rid of this mod, because this I am returning mod, right? I am returning mod here. Let me return mod here also, so that I don't have to do these mods. Okay, don't have to do these mods. Okay. So you see, you have this, right? This inverse factorial into factorial. Try to store it in long. Always when you are multiplying, try to store it in long, and then perform a mod. These things must be performed before this thing, right? So you get another bracket here. You give another bracket here to perform this mod, and this is nothing but this. Okay, this is nothing but the last bracket. You just see this as the whole as LL again, and then you calculate whole mod. I hope you get what I am doing, right? I hope you easily get what I am doing. Do I have an extra bracket over here? Yes, I did have. So at first, I'm just calculating this mod, okay? I have the NCR ready with me. I need M and M minus 1. There is nothing. So I just calculate this power value. It's nothing but binary exponentiation of a to the power b. I need to write a to the power b, m minus 1, n minus k minus 1. M minus 1, n minus k minus 1. I have this also. Okay. Now what I need to do is simple. I need to just return NCR into M into power. But oh wait, you cannot forget the mods at any cost. Cannot forget the long as well as the mods at any cost. Okay. You do get it, right? These mods and long, you cannot forget it, otherwise there will be errors. So you have it. You have the result, I guess. You have M, you have power, you have everything with you. Let's try to run it and check if there is any error. Network error. Just a second. So I have done this mistake anywhere. Yeah. Okay. This cannot be stored in integer. I told you always store in long whenever you are multiplying. It's taking too much time to run. I don't know why. It's just taking way too much time to run. Again, here is a multiplication here. So you need long wherever there is multiplication. Let me check the whole thing again. Yeah, you see, we do have the accepted thing now. Let's try to submit it. Yeah, so we have the accepted thing. So that was all. That was all for this problem. This is a hard problem if you don't know much about this inverse factorial or binary exponentiation. And if you have done enough conversion and combinations in your class 11th and 12th, I guess this is simple. It should be simple. This is just one formula. You just derive it. Okay. So that's all. That's all for this problem. And I hope your day goes really easy. Thank you so much.